Now let's take a few minutes here to look at some properties of the definite integral. If f and g are integrable on a to b, and k is some real number, then k times f and f plus or minus g are also integrable on a to b. So here's some properties, and let's fit around with this and keep these in mind as we take a look at a couple of examples here. Now this first example is kind of a special situation. The integral from a to a of f of x dx is actually always going to be equal to 0. Now we can reason that out. I know if I go from a to b and I integrate this from a to b, that will give me the area under curve between a and b. Oops, I kind of missed a over here. Okay, but what if I go from a to a? I'm at a and I don't go anywhere. Well, all I have here is the area under the curve, which amounts to this line. But lines have no thickness. They have no density. They have no mass. You can only see it because my pen has width, so you can actually see it. Now, if you think of this in terms of a rectangle, I'm going to have a height of f of a, and that gives me the height of this. But there is no rectangle. There is no width. So my width is 0. So this is like f of a times 0, which is 0. So this integral will always give me 0. Now, the integral from a to b of f of x dx is actually equal to the negative of the integral from b to a of f of x dx. So let's see what that means. Again, let's go back to this basic picture. Seems to serve us quite well. What this is saying is if I go from a to b, left to right, I will find the area under the curve. But if I go right to left, what that actually gives me is the negative of the area under the curve. So if I take the negative of a negative, that's a double negative, that gives me a positive. So integrating left to right equals positive. That's assuming, as we said earlier, that this function f is positive, or 0. From a to b, it's positive everywhere or 0. That's not negative anyplace. So if I go left to right, I get a positive. If I integrate right to left, in other words, b to a, that's going to give me a negative. Absolute value of b to a is equal to a to b. So take the absolute value of the negative, and it's going to be the same as the positive over here. So in other words, if I integrated this, and this was equal to, say, 2, and if I integrated from b to a, this would give me a negative 2. Well, the absolute value of negative 2 is 2. Now, remember we said that k is a real number. That's just some constant. This integral, which is kind of nice to remember, is simply equal to k times the integral from a to b of f of x dx. Now, that's a nice property to remember because if we pull out a constant and didn't finish your integration, quite often the integration itself will be much easier than leaving the constant in. So being able to pull that constant out, it makes sense. I mean, it really helps. Now, in terms of a picture, this kind of makes sense. If here I go from a to b again, so this is f of x. If I multiply f by k, where k is a real number, and actually I should say positive real number, because if I multiply by negative, it come down here and everything kind of changes. So I really should say k is an element of the positive reals. Well, k times f of x, specifically for k greater than 1, is going to be up here somewhere. It's going to be the exact same looking curve. It's just multiplied by k. So every point gets multiplied by k, so it's k times bigger. So what happens? The area gets k times bigger. Now, on the other hand, if 0 is less than k, which is less than 1, then I'm going to have this function is going to be shorter, because every value in here would be multiplied by a fraction between 0 and 1, so it would be reduced by that amount. either way, intuitively, it seems to make sense that if I can find the integral of f of x, find out the area under the curve, then simply multiply it by k. That's going to give me the total area under the curve of k times f of x. Now, the integral from a to b of f of x plus or minus g of x dx is actually equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Actually, I should say plus or minus, because all I'm going to do, I'm going to add up the area of both these curves. So, as an example, if I have, again, from a to b, suppose f of x looks like this. So it would give me this area. And let's see, label this. This is f of x. And then suppose g of x, change colors. G of x, maybe it looks like this, which should give me this area. Well, the integral of f of x plus g of x is going to be all the black area plus all the blue area. I'm just adding up the area from both functions. So again, hopefully that would seem somewhat intuitive. Now, the integral from a to c of f of x dx is equal to, well, let me draw you a picture first to make sure it may make more sense if you see where we're going. If I think of this as area under the curve, the integral from a to c is going to be all that. But if I need to, I know I can break this up as the integral from a to b of f of x dx, where b is in here someplace, plus the integral from b to c of f of x dx. So the first piece would give me from here, and this second piece would give me here. And it should be obvious if I add them up, I will get the same as a to c. Now, that may seem kind of odd, but it actually is important because we're going to look at some examples where we're going to have to break them up to get some meaning out of it. So we're going to have to do separate integrals. Well, here's another theorem, and it should kind of make sense. If f and g are both integrable on a to b, and f of x is less than or equal to g of x for all x on a to b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of gx dx. Well, let's do this. Again, let's do this curve. And let's suppose that this is f of x. Well, f of x, if I integrate this, is going to give me all this area. Now let's pick g of x, and g of x needs to be greater than or equal to f of x everywhere. So it could be equal, so maybe we're equal right there. Every place else we're greater than. Well, g of x is going to give me all of this area. So it should seem somewhat intuitive, let me label that as g of x, that the integral of f of x from a to b is going to have less area than integral from g of x to a to b, because g of x is bigger than or at least equal to f of x everywhere from a to b. So that should not be too much of a surprise. And this last little guy here, if f is integrable and non-negative, that's kind of important, on a to b, then 0 is going to be less than or equal to the integral from a to b of f of x dx. So all this is really saying is, again, if I have some curve from a to b, if f is integrable, so it's continuous, and non-negative, so I could be 0, come up, come down, be 0 again, come up, whatever I'm going to do, I'm non-negative, then I have an area here that's always going to be greater than or equal to 0. The only time it's going to be equal to 0 when f is non-negative is if f of x happens to be equal to 0. That would be flatlined right there between a and b. It is the x-axis between a and b, and there's no area between the x-axis and the x-axis between a and b.